recent work DeFog, Discrete matching for graph generation. And I would like to start by introducing the team. We are a team of researchers based on EPFL in Switzerland. Yiming and I, we were both PhD students, and we were supervised for this work by Dorina Tanu and Pascal Fossa. Yiming and I, despite other scientific endeavors, such as for model merging or training foundational models for scientific applications, the main topic of our PhD has been on graph generation. So we would like to start by giving you a picture of the landscape of graph generative models. So generative models in general at this point need no introduction anymore. They have been used. They've been adopted by the general public by the excellent image, video, audio, diffusion, text models that have been provided by different companies. But for many real applications, data is structured, and therefore, for instance, in the case of molecular generation, we want to understand whether and how the different atoms interact, so that we can build new molecules that are not in our training set. In the case of circuit design, we want to rearrange the electronic components to optimize given criteria while still adhering to some physical constraints. In the case of network modeling, we want to understand how diseases propagate through contact networks, or for instance, in the case of epidemics, or for instance, in how information spreads through communication networks in the case of social media. Therefore, graphs are very convenient to model all those settings and many others because they naturally model relational data and capture non-Euclidean structure. So what I'm saying is that graphs can be used to model data defined over irregular domains and that need no global coordinate system. Therefore, graph generation becomes as the same formulation as other data modalities. We want to sample more graphs that resemble those in our data set. What I mean is that we'll have an underlying probability distribution from where we assume that the graphs in our data set were sampled from. And we want to sample more graphs from there. But the problem is this probability distribution is unknown, making this problem non-trivial to solve. The first approaches to this problem were based on random graph models. So basically, you would assume a predefined random distribution, as is the case of Erdős running models, where an edge is sampled with probability P between every two nodes, or in the case of Barabasi-Albert model, where each new node, so basically we are progressively growing our graph, and each new node connects to m existing nodes proportionally to their current degree. Importantly, these models are not adaptable to the data. So basically, we could kind of tune our P or our M to the data we have. However, they have a strong prior over the type of graphs that they can approximate. Therefore, deep learning-based approaches emerged as able to capture intricate graph distributions. The first generative paradigm where these type of approaches emerged was in the autoregressive paradigm, where you progressively grow your graph by inserting nodes and edges until you have your final graph. However, this type of approach assumes a node ordering, which is a notion that graphs inherently lack, making this approach impractical. Alternatively, one-shot models were also adapted from other data modalities, such as variational autoencoders or GANs, where we sample a latent vector from a random distribution and we decode it in one shot to a full graph. This type of approach dodges the problem of the node ordering, however, still faces challenges as solving matching problems within the formulation. So this ends up hindering their generative performance. Recently, an alternative paradigm emerged, diffusion models, in particular for images. And the main idea of this paradigm is that you progressively noise your clean instances. So you have clean images, and you progressively add Gaussian noise, and then you try to denoise it so that at inference time you just start from full noisy images, and by running the denoising process, you would end up with fresh new samples. However, the problem is that the distribution that models this denoising process is not tractable, and therefore we have to learn. We use a neural network to approximate this distribution. Diffusion models offer several advantages over previously existing paradigms, such as in comparison, for instance, with autoregressive models, they typically provide faster inference because we have less denoising steps than the data dimensionality, for instance, the number of pixels or the number of tokens in a sentence. in comparison to GANs, you have more stable training, and in comparison to VAEs, you have a more refined generative process that enables a better generative performance in the end. Naturally, diffusion models were adapted to graphs, and they, again, are based on this iterative refinement idea. And the main innovation in the case of graphs is that we can track every node and edge throughout the noising and denoising processes. The fact that we can do this track now allows us to design a permutation or invariant formulation, which means that whichever is the computational, we can learn representations. So whenever we need to put the graph into the computer, we have to set an order for the node. So basically, we are assuming a node ordering. But the representations that we learn throughout this type of formulation become invariant to the permutation, so basically to the node ordering that we assume in that implementation. And besides that, they also enable state-of-the-art generative performance. So to give some examples, we had initially the ADP-GNN diffusion model, which was based on the initial diffusion model framework that I just presented before, and it consists of adding progressively Gaussian noise, but still under a permutation invariance formulation. And you can see from these examples that they are already able to capture much more diverse graphs than the Erdős-Renyi models or the Barabasi-Albert models. More recently, Digress was for a long time the state-of-the-art graph diffusion model, and it was also widely adopted for different applications, because from the samples that I'm showing you, you can see that this model already can capture quite complex graphs. Besides this, graph diffusion models can be categorized taxonomically along two main axes, one defining the time and the other one the state space. So initially, as I mentioned before, we had EDP-GNN, where we have a continuous state space. So we assume that the variables lie in a continuous state space, and we add Gaussian noise over them. And in terms of time, we have discrete time. So basically, we always go throughout the same steps. Then a first extension provided a formulation over continuous time. This allows you a more robust training, because now you're not stuck at the discrete time steps that you defined before. And also it allows you a more flexible sampling, because you can play with the time step of your throughout your sampling process, allowing you to further boost your performance. In parallel, a formulation based on a discrete counterpart of diffusion, so basically discrete diffusion, also emerged, and it natively allows to align the formulation with the inherent discreteness of graphs, and thus allows to preserve the topological characteristics of graphs, further pushing performance. Therefore, before DeFog, the previously existing state-of-the-art consisted of methods that combine these two improvements, so working on discrete state spaces and running on continuous time. However, the training and sampling of these graph diffusion models were still highly entangled. And what I mean by this is that it constrains training time choices at the time would constrain the sampling design space. So if you wanted to tune an hyperparameter at sampling time, we would need to retrain the full model, and this would limit the adaptability of graph diffusion models to different graph datasets. And note that this is particularly problematic in the case of graph datasets, because they are really used to model instances of very different natures, for instance, molecules or circuits or social networks, as I mentioned before. And therefore, now introducing DeFog, this is the main motivation for DeFog. Besides the existing taxonomy, our contribution is in an orthogonal direction, where we seek to decouple the training and the sampling processes of the method. So in order to accomplish that, we build our formulation still in the discrete state spaces continuous time, so that we can benefit from those settings. But we use a different formulation. We build upon the discrete flow matching formulation, or DFM. And this formulation is based upon two main processes. First, the noising process, which in this case, we will set to run from t=1 to t=0. So at t=1, we have fully clean data, and t=0, we have fully noisy data. And the noising process will consist of a linear interpolation between these two distributions. So you see in the image now, where I have my cursor, you have the clean data, and you see that the data point was at the green state at the time. And on the left, you see that this will be our noisy distribution, or initial distribution, which consists of a uniform distribution and is predefined by the user. So we could set any other distribution here. And then for all the other time instance, we just set a linear interpolation between them. Then for the denoising process, we will try to revert the denoising one. So it is formulated as a continuous time Markov chain and is governed by a rate matrix. This rate matrix basically defines the instantaneous transition rate of states. So basically, if I'm in a given state, it will give me the instantaneous transition rate to other states or even to the same state. So basically, the progress of a CTMC can be modeled by this update rule that I'm now highlighting with the cursor. And the main idea is that given that I'm at state ZT, at time step T, what is the probability of moving to the category ZT plus DT at time T plus delta T. And this expression, which might seem a bit weird right now, I would like to first do a parallel to another step that might be a bit more usual for a general audience, where we have that the updated function will consist of the function at the previous iterate plus the derivative of the function at the previous iterate times a time step. And we can see things as a parallel of this term. So for the value of the function, we have this Kronecker delta. So it's basically the state that I was at ZT. It's 1 at that state and 0 for all the other states. And then the rate matrix gives me the instantaneous transition rate to whichever states. Note that for the notation I'm using, this is the state where I am right now, and this corresponds to the state that I'm moving to. Nevertheless, once we have this update rule, it's still unclear how to compute RT, and this is the main punchline of discrete flow matching. So basically, the idea is that we can to compute this rate matrix, this unconditional rate matrix, it turns out that it is easier to consider the conditional rate matrix on the endpoint. Because if we do that, then we can derive a closed form for this conditional rate matrix. And then after, of course, we have to compute this expectation. And we use noticing that this probability distribution corresponds to predicting the clean data given the noisy instance. So I've introduced before for the diffusion model, this is typically what is done with a neural net, right? So we will try to learn this probability distribution of the clean data given the noisy data using a neural network. Therefore, provided this background, how do we actually adapt this formulation to graphs? So how we proceeded was, first, we will noise independently each node and each edge. And then for the denoising process, we will have to simulate a multivariate CTMC. So basically now we have several nodes and several edges being denoised at the same time. And doing this type of simulation is quite complex and typically, if solved exactly, is quite expensive as well. So an approximation that is typically done is to update each variable independently. In our case, each node and each edge independently. So abusing now a bit of the notation, what I mean now is that our update now, instead of being solely based on the previous value of the node, so basically I'm denoting here n as the xn as the class of the node, and instead of only considering the previous value of the node, I'm considering the full graph. So I will use my full graph in order to have a prediction in order to have an update for my node. So basically, again, I have this delta on the state where I was, and I have a rate matrix. And again, I'm abusing the notation here. But what I'm saying is that for the computation of this rate matrix, I will consider that I can have a look at the full graph. And then I will use this full graph to have a prediction. And this will be computed again to have my update for the next time step for my specific node. So it might look a bit blurry at this point, but I hope it will become clear in the next slides. So once we define these, we can actually look at how we train our DeFog model. We first sample a graph from our data set. So this consists of a clean graph. And then we sample a time step from a distribution covering from 0 to 1. Note that this distribution is arbitrary. Typically, it is assumed to be uniform, but other distributions can be considered. And once we noise the graph, then we will pass it through a graph transformer that will predict for each node and each edge a probability vector. So what I'm saying is that, for instance, for this edge, I will predict a probability vector that lies in the simplex of dimension e plus 1, so e being the number of edge categories and 1 being the no edge state. So I will assume actually that between every 2 nodes there's an edge, and one of the edge types that I can have is no edge. And I will proceed similarly for nodes. I will have a probability vector for each node, and this probability vector will lie in the simplex of dimension being the number of categories that we have for nodes. Then, once we have this prediction, we just set the cross-entropy loss between these probability vectors for every node and every edge between predictions and clean graph. Then we just repeat this process repeatedly until convergence of our parameters.
Just one quick question. So yeah, it's only for the nodes. It's only the class, right? You don't consider 3D. So XY.
Yeah. So here I'm assuming it's just and in our until now all our implementation just runs on categorical data. So we never consider continuous data, which would be the case of
right.
Of 3D coordinates, but it should be easily extendable. Like there are works that would, for instance, the previous method that I mentioned, digress, was also initially also proposed only for categorical data, and then it has been extended to integrate the 3D coordinates. But yeah, for now it's just categorical data.
Okay.
Yeah, I forgot to mention, but yeah, feel free to interrupt whenever something is unclear or you're curious. Thank you. So yeah, one of our contributions is also by theoretically grounding the training loss that we use. So we use the same training loss that was previously used for graph diffusion models. We apply cross entropy between nodes and edges. But the main difference is that this time we are able to motivate it theoretically. So what we actually do is that we are able to upper bound the estimation rate error of the rate matrix that we will use to denoise throughout the denoising process. We upper bound this by a term, like two terms, one term that is constant and the second term that is, I mean, here all the C's are constants, and we will have here implicitly the loss that we actually use for DeFog. So what I mean is that for L node, we will have the cross entropy between all the nodes, and then we will have a weighted version of the loss between edges, or again, cross entropy between edges. Note that this constant then can be used to weight differently edges and nodes, of course, and this allows us to be more flexible again in capturing the different topologies. Once we have our training model, we can sample. We can sample, or we want to sample from our DeFog model, and the main idea is that we start by sampling a graph from our initial distribution. So this is predefined and should be an easy distribution, so it's pretty straightforward. And then once we have our initial graph, we just keep applying denoising steps, and I'm now going to exemplify what the denoising step should be. So I will exemplify for the case of the top node that is highlighted in light gray. So the main idea is that given the full graph, our transformer will predict for every node and for every edge, but in this case, let's focus on the case of the top node, a probability distribution. And given this probability distribution, we are then able to design a rate matrix according to the closed forms that we mentioned before. Then we just have to combine the rate matrix that we just computed with the actual state of the 1 watt representation of the state where the node was, and we get the update probability vector. We sample from there, and now we have our new node class, so our new node category. And this becomes, we proceed like this for every node and every edge, and we are able to get our one-step denoised graph. We proceed iteratively like this until we get to the fully clean graph G1, and this consists of our new sample. So what does this sampling method actually look like in reality? I'm now showing you a GIF of sampling for a community-based dataset, so for SBM. And the main idea is that you'll see the graphs progressively, the communities progressively being formed with much less connections across communities. And then also for the case of a molecular graph, we will see that progressively DeFog also learns how to generate a molecule that looks realistic. Another contribution of our work is also by theoretically sampling, theoretically grounding our sampling process. So what I mean by this is that considering that we have an initial distribution P0, and we run the ground truth process, so we would end up in the ground truth distribution P1, and then alternatively, we would run our denoising process, which has several approximations. For instance, we use the neural network, we discretize the simulation of the CTMC, and there's another one, but there's another approximation, which I'm not recalling right now, but it will come in a moment. And basically, the idea is that you're able to set up an upper bound on these, on the distance, to some notion of distance between these two probability distributions. This upper bound is composed of mainly two terms. One is a constant term coming from theorem 1, so basically from the previous result that I showed. So basically, the lower our training loss, the lower this term becomes. And then a second term, which tells us that the error that we incur by doing this discretization, this series of approximations is controllable by reducing the step size that we use. Finally, we ensure and leverage some graph-specific properties in this formulation. First, we demonstrate that by adapting the DFM formulation to this setting, DeFog is able to respect graph symmetries. In particular, DeFog is the DeFog model. So basically, the graph transformer we use is permutation-equivariant. We also demonstrate that the loss function is permutation-invariant, which basically is a result of just tracking node per node and edge per edge. Basically apply cross-entropy node-wise and edge-wise. That's what I mean. And as a result of these two premises, the sampling probability of a given graph is also permutation-invariant. Then finally, we also leverage some extra features to enhance the expressivity and the efficiency. In this particular case, we used we used powers of the degree normalized adjacency matrix, which is defined as in the slide. But the main idea here is that we use these extra features to enhance the expressivity, and in comparison to previous works, the computation of these features is much faster. So basically, for the case of digress, that these type of extra features consist of these two last columns where spectral features and cycles would be computed, and now with our RWP, we are able to get better performance in much less time. And so now I'll pass my word to my colleague Yiming that will proceed with you for the rest of the presentation.
Hi. Thanks, Manuel, for the previous presentation. So now we already have discrete flow matching based graph generating framework. And how does this framework actually perform on graph generation? We use one of our sanity graph data sets, planar graph data set, as an example. In this graph data set, we only have graphs with no edge crossings. And to evaluate this data set, we will use two important metrics. The first one is called VUN, that measures the topology correctness of the graphs. Here it means if it's planar graphs. And the second one is ratio, which measures the distributional distance. So we will expect intuitively VUN to be as high as possible and ratio to be as low as possible. So if we look into this table, actually the vanilla DFM will work similarly with diffusion models represented by digress. Well, this means that discrete flow matching models does not really work out of the box better. However, for our model, the cool part is that its training and sampling process, as mentioned by Manuel before, are highly independent. So we could actually recall the training and sampling process of DeFog. In training, what we are actually doing is to sample T from a distribution from 0 to 1. And then we will optimize this model by learning the cross entropy by predicting the clean graph distribution given the noisy graph distribution. And in sampling, we will split the generation from T equals to 0 to T equals to 1 into small sample steps delta T. After this, we use a rate matrix formulation to progressively denoise the graph based on the model output. It is actually important to remark that both of the time distribution during training and the sample step delta T, or the formulation of R, they are inherently independent among them. This means we can train each of them separately. This unlocks the design space of DeFog by far. Based on that, we explored mainly 4 ways to improve DeFog performance during training and also during sampling. During training, we will explore how to choose properly this distribution of T by a method called train distortion. During sampling, we will try to understand what is a best way of choosing the sample steps delta T, and we call it as sample distortion. After this, we also leverage 2 methods that controls the stochasticity level of the generation and provides additional guidance toward the Cartier distribution by modifying the rate matrix R, which is used to control the denoising process. So let's start by the sample distortion. If we consider the generation process, for example, if we are generating a graph with 5 steps, typically people will use equal intervals during inference. That means for every step, I will move on for 0.2. However, we can actually apply any strictly increasing bijection function f from 0.1 to 0.1 to reshape this step. For example, we can consider ft equals to 2t minus t squared. And this function actually makes the time steps during inference much more focused on the later stage of generation. In the same spirit, we also explore different types of distortion functions as shown in the left on the right figure. After this, we can also use the same type of distortion functions during training stages. During training, we typically sample T from a uniform distribution of 0, 1, which is actually represented by the curve, the green curve here. So here it's like the density map of this distribution. And by adding this distortion function, what we are doing is actually to concentrate the training on certain time intervals by distorting the time distribution during training. For example, if we apply the function called polydec, what it actually does is to make the density function much more concentrated on T larger than 0.8. So this function actually directs the model's attention during training to refine later stages of the inference. After this, let's talk about how to modify the rate matrix. The first way of modifying the rate matrix is within the space that's still verifying the Kolmogorov equation mentioned by Manuel before. So if we denote R star as the base formulation we are using in DFM, it is actually not a unique solution for this equation. Actually, if we consider another group of metrics that we call RDB, which verifying this equation, which is called detailed balance, then any matrix which is R star plus eta RDB, well, eta is like a positive scaling hyperparameter. These new metrics represent a more general group of valid rate matrices. So how does this eta RDB actually functions? In fact, in the original denoising process of DeFog, it's not super dynamic. Imagining if we have a wrong H-type at this stage of the generation. So the real type is actually not C, but something else. Then we will stuck in this wrong type prediction. However, if we have a higher eta, what it actually do is to have leads to a more stochastic generation process. So in this case, we can actually have more modification, a more chance to modify this wrongly sampled H-type, and we can, in the end, have the correct prediction. So this means that this stochasticity term, RDB, allows better error correction in the denoising process. In this figure, we observe that by incorporating this stochasticity, which is skewed by eta, we can significantly improve the generation fidelity, which is related to smaller ratio. However, we also observe that there exists trade-off. So if we have no stochasticity at all, the ratio will not be super satisfying because there is no error correction. But if we have too much excessive stochasticity, the performance will also become worse because the dynamic of the denoising process will become too random and stochastic. In the end, we want to mention another method called target guidance. So target guidance is mainly inspired by this figure. In this figure, the y-axis means ratio, the previous matrix we have introduced. And lower ratio means that the generated distribution is closer to the ground truth data distribution. And the blue one is the vanilla DeFog generation. So we can see that the denoising process is not very smooth, and it actually has a sudden transit after t equals to 0.8. This means that the denoising process for 80% of the time are not very effective. And in real life, we really want to have a smoother generation process, and we want the generation process to be effective at early stages. To realize so, we actually add some extra weight that is referred to as R omega towards the original base rate matrix R star. And this R omega is actually adding more weights to the predicted clean graph distribution. So in this way, this method is still inherently different with the previous stochasticity method, because adding this RDB used in stochasticity does not violate the Kolmogorov equation, but adding this R omega actually is guiding the distribution to the clean data distribution. So it actually violates this equation with an error of O omega. This figure also shows that the target guidance will significantly decrease the ratio metric, reflecting better graph generation quality. Similar to stochasticity, there exists a trade-off. If we don't have target guidance at all, the ratio would be high because the denoising process is not effective enough. If we don't have any target guidance, if we have excessive target guidance in the end, the ratio would also be high because we are inherently distorting the distribution since we break the Kolmogorov consistency. In the end, we have the same conclusion. We have to choose appropriate target guidance level to have a better performance. So before I go to experiments, is there any questions regarding the previous slides, or I can also go on?
Just super quick, the ADA, is that like a ratio, or like how far your training distribution is from your generated distribution, or? Oh, sorry, not ADA, my bad. The ratio metric.
Yes, the ratio matrix actually measures the distance of some important graph statistics between generated graphs and the ground truth graphs. So if it's lower, it means we are more distributionally closer.
Okay.
So with all those improvements in place, let's take a closer look at how DeFog actually now performs in our experiments. To have a comprehensive evaluation, we consider three types of tasks. The first task is standard graph generation, and we consider three types of graph data set with different types of topologies, for example, planar graphs. As we have seen before, this type of graph does not have crossings inside. And the second graph data set is to mimic the clustering behavior of nodes, and the third is tree graphs. Second, we consider molecular graph generation, and in molecular graphs, we have richer nodes and H-tabs to represent different, sorry.
All good.
Okay. To represent different types of atoms and valence bonds. And in the end, we also test the performance of DeFog on conditional graph generation. Here we consider a special graph dataset extracted from tissue images that have some certain biological relevance. Based on those relevance, we can group those graphs into either low TLS content, either high TLS contents. So in the end, we want to do conditional generation based on those two types. So let's start with sanity graphs. Here we consider three datasets, planar, tree, and SBM. And we have two important metrics, VUN and ratio. As we can observe in this table, we have high VUN on three of those datasets. It means the model is able to learn the correct topological structure. At the same time, we have low ratio, which means that the generated graphs has low distributional distance with the ground truth graphs. Another important thing to remark is that we also have the result of DeFog with only 5% of the generation steps. This means we actually accelerate the sampling by a factor of 20. So here, with only 5% of steps, we still have higher performance. For example, on planar data set, we reach 95% of planarity, which surpasses almost all the previous models. For molecular graphs, we have the similar observations. So we consider two data sets, Guacamole and Moses. For Guacamole, we reach the best performance compared to all its diffusion counterparts. And then for Moses, DeFog reaches the best validity and SN score. And in the end, we also measure the performance of DeFog when we are generating with less number of steps. So here, we consider the situation when it's 10 times faster. When it's 10 times faster, we can have a validity of 91.7 on Guacamole, which surpasses the previous baseline digress using diffusion models. In the end, let's take a look into digital pathology graphs. So for this, we are basically generating graphs with either low TLS content or high TLS content, which reflects certain cell organization structures. The important metrics for this dataset is VUN, as before, and TLS validity, which measures if the conditional generation is effective. So on VUN, DeFog is only worse than one of the methods that is constrained to generate planar graphs. So this type of method is designed specifically to generate planar graphs. And on TLS validity, DeFog reaches the best performance. That means the conditional generation with classifier-free guidance is functioning well with this model. So beyond numbers, we now want to have some qualitative impact of the proposed sampling and training optimization method. First, we want to show that this method improves the sampling efficacy by far. We illustrate this efficacy gain with this figure. If we look at this figure, we have the same observation as before. A vanilla DFM does not working out of the box better than diffusion models, such as digress. But by adding all those previously mentioned techniques, such as sample distortion, target guidance, or stochasticity, we can improve the performance on each of the steps. If we look steps equals to 1,000, after adding all those steps, we reach the final performance of DeFog, which is 99.5 on planar datasets. And if we consider less number of steps, with 50 number of steps, for example, those benefits of those proposed strategies is even more evident. For example, by adding only sample distortion, we can change the VUN from 10% to 70%. And after this, we can add target guidance on top of that. With only those two strategies, with 50 steps, we can already have a better performance of than digress with 1,000 steps. In the end, we also want to mention that the proposed method also improves training efficiency. So we have the same observation as before in this figure. So this figure shows a convergence of Moses data sets with respect to the training time. So the vanilla DeFog DFM model does not function better than digress model. But if we add those optimization methods, for example, the sample distortion, we can already improve the convergence by far, since now we have better generation performance. Another interesting comment is that when we find the best sample distortion function only during inference time, we can reuse this distortion function in training, because actually this distortion function, it identifies the critical time intervals for sampling. So if we can actually focus the learning on those critical generation phases, we can have even better convergence. So this is the final curve we show. By adding the train distortion based on the same distortion function used in sampling, we can have a quicker convergence. And in the end, I want to conclude for training efficacy. The first good part of that is that we don't need to do extensive retraining. So the best distortion function, which is similar to the noise schedule used in diffusion, it was selected during inference time. So we don't need to retrain the model for every of the configurations. As the second part is that if we have limited computational resources, for example, the model can only be trained with 10 hours, even the original result would not be perfect. It would be 70% second. But by adding those sample strategies, we can already have a very good performance. For example, here we can reach nearly 90%. So this means we can reach high performance with sampling optimization method for undertrained model. Sorry, it should be under-trained model.
One quick question.
Yeah,
So
sure.
you say that you reuse the sample distortion scheduler, let's say, for training.
Yes.
But so that means that you started with one in training, then you tested different sampling ones, and then you took the best one to retrain?
Yes, this is one way of doing that, but for most of the data sets, we are not doing this double retraining. It's just for Moses and guacamole because those two data sets are large molecule data sets. They take a very long time to train. So the training distortion will be very helpful to accelerate the training process.
Okay, and when you reuse this new scheduler, will the sampling distortion scheduler change, or it would keep being the same one?
We have a heat map to show the interactions of training distortion and sample distortion. Typically, if we just train with uniform distribution, and we can already find some sample distortion that works much better than the equal intervals. But typically, if we add the training distortion in training time, then typically it would be functioning better if we have the same function for training and sampling at the same time.
Okay.
Is that clear?
Yeah, thanks.
Okay, thank you. So I will go on. To finalize the presentation, we will now summarize the main takeaways of this presentation and look towards what's next. So the most important observation from DeFog is that the decoupling training and sampling phases for discrete flow matching models is very important because it opens up a lot of new possibility to optimize the sampling stage and also the training stage. Among the 4 methods we propose to improve DeFog performance, sample and train distortions, they function very similarly to the noise schedule as in diffusion models. However, they can be tuned during only inference, which allows much better exploration and much cheaper exploration. And another 2 methods, stochasticity and target guidance, which is used to modify this rate matrix, also leads to much better generation performance, especially when we have fewer generation steps. And take a better advantage of both of those methods, we have to set appropriate intermediate values for both stochasticity and target guidance. So after this, we will just discuss briefly potential possibilities to extend DeFog for broader applications. The first thing is, as the previous question, we can expect DeFog to support both continuous and discrete node and edge labels. This type of incorporation of geometric features of, for example, 3D coordinates has already been validated in the domain of molecular generation. The model MIDI, for example, it can generate both the graph structure and also the 3D coordinates together, separately using a discrete diffusion and also a continuous diffusion. The same type of progress can also be expected in other chemical structures, such as crystals, since the coordinates also reflects its arrangement and is also important to understand the interactions between the particles inside. We also hope to call for more real-world benchmarks beyond small organic molecules. Typically, for structures of material similar to organic molecules, they can be modelized by graphs with different type of atom types and also for different type of bonds. And for this type of applications, graph generative models can potentially be used for material discovery and also for material optimization when we actually want to optimize or generate certain structures based on certain chemical properties, for example. Another possible way is for particle interactions. For example, here, there is a map for different type of particle interactions. And this type of interactions can also be naturally modeled by graphs. And generative models for graphs can potentially simulate particle interactions and produce the configurations conditioned on different type of phases and different thermodynamic conditions. So that's the end of our presentation. So thank you a lot for your attention, and we'd be happy to take any questions you may have.
Thank you so much. If there are any questions, you can write in the chat. I have a few questions on just more broadly on flow matching. Is there like a condition inversion like in diffusion? Like you have classifier-free guidance and stuff like that? There is, right?
Yes, for classifier-free guidance, DeFog already supports it by default.
Okay.
But for more difficult type of conditions, if the condition is like more than a category class or like more than a scalar, then there might be more difficult considerations need to put inside to optimize the generation performance. But now by default, it already supports conditional generation.
Okay, so conditioning on, say, an embedding, it would be a bit harder than just regular.
No, it should be the similar things.
Okay. I was asking because nowadays, I mean, say for like molecules, which is like my topic, I see a lot of models on that use diffusion instead of flow matching. And I was wondering why, and that's what another like one question I had. Yeah, because like most of the newer models are just diffusion, and they don't see, and like what you show, like you can see that there is a lot of improvements over diffusion that they could leverage. Do you have any comments on why? Do you know?
I think it might be just an historical artifact, let's say, because diffusion models emerged first, right? So they,
right, yeah.
Most of the literature for conditional generation, I guess it was targeted at diffusion models. Meanwhile, flow matching models emerged, and they are still catching up. But I don't see any fundamental reason for the conditioning methods that are applied for diffusion not to work for the case of flow matching, except, I don't know, in very dodgy cases. Like, I don't want to generalize as maximum as possible, but in principle, I think both methods would be applicable. I mean, conditioning methods would be applicable for both. But my point is, are you talking about like discrete versions or continuous versions?
Yeah, I was going to mention that both. Yeah, it would be on when you do both at the same time.
Yeah, like from the discrete setting. So we tried with both, and what you do for one works for the other one, like out of the shelf. For discrete flow matching versus discrete diffusion. For the continuous setting, I'm also not aware of any setting where it would not be applicable. I'm just not as confident because I don't have as much experience, but on top of my head, I don't have any example where that would be the case. I don't know if you had any experience with that.
No, I've always used diffusion. That's why, like, I've always looked at flow matching like on the side because, like, I'm not super familiar with it. But yeah, like all the examples I see is just diffusion, and I mean, just from like reading and so on, I don't see either like why they wouldn't use flow matching.
Yeah.
Like for biology, for like proteins and so on, there's I think one big model that uses flow matching, and all the rest are diffusion. So yeah, I don't know why.
Yeah, I think it might be like historical reasons that are. Yeah.
Yeah. I mean, they have a few more years, I guess, ahead of.
Yeah.
Okay. Well, thank you so much again. I don't think there are more questions. So yeah, again, thank you so much. We'll be posting it on YouTube, and yeah, it was nice to have you guys.
Okay, thank you.
Thanks a lot.
Thank you so much. Bye.
Nice day.
Ciao. Nice day.